So far in this section, we've identified three types of turning point: the local maximum, which is this shape, the local minimum, which is this shape, and the horizontal point of inflection, which is either shaped like this or like this. All of these points are characterized by the gradient of the tangent to the curve at the point being 0. So at all of these types of turning point, dy dx is equal to 0. In order to identify turning points, we can use sine tables. The sine table will always work for all three types of turning point. Using a sine table, we can tell if we have a maximum, a minimum, or a horizontal point of inflection. The drawback with sine tables is that they can take a long time to do, especially if dy dx is a complex function which we have to substitute numbers into. The other way of identifying our types of turning point is to consider the second derivative d2y dx squared, which we get by differentiating dy dx. We would then evaluate d2y dx squared at the turning point, at the x value for the turning point. If d2y dx squared is less than 0, we have a maximum. If d2y dx squared is greater than 0, we have a minimum. The drawback with this method is that if d2y dx squared is equal to 0, it could be any of the types of turning point. So if we get d2y dx squared is equal to 0, it could be a maximum, or a minimum, or a horizontal point of inflection. However, using d2y dx squared is much quicker than using the sine table. Since d2y dx squared is generally quicker, my approach usually is that I evaluate d2y dx squared, and if I get one of these two, I've actually identified whether I have a maximum or a minimum. However, if I get d2y dx squared is 0, which tells me nothing, I then use a sine table to see which type of turning point I have.